Okay, so just as a reminder, if any questions come up, of course, feel free to raise a hand, put something in the chat if you're online, or regardless of where you are, if you want it to be kind of anonymous or just kind of cached in a queue, whenever these slides come up, you can feel free to follow the QR code or the link and leave an anonymous question there. If I catch it during class, it's great. Otherwise, I'll answer it online. Other more general, I guess, or maybe more specific reminders. There's, for those working ahead, if you would like, so homework B1 isn't technically a released, because it sort of released when we hit lecture B1, which will be next week, but it's available. So if you're reading ahead and you want to start on that, the first half of homework B1 is a lot like lab 1. So if you've done lab 1, then you're probably well prepared for homework B1. Lab 2 is a lot like the second half of homework B1. So those are available in case you want to work ahead. There's this ICA that'll be due, I think, pretty much a week from today, lecture B2, just 5 questions. And again, these ICAs, they're going to be several of them. So like, I don't know how many I said there were, like 12 maybe throughout the semester, but you drop below 7. So they're just trying to give you an opportunity to stay connected to the material, but if you're already overloaded with everything else, you only have to complete 5 to contribute to your score. So I'll keep reminding you of them, but I don't want you to feel overloaded by them. They're just meant to be opportunities. Okay, so any questions about any of that before we move on to new stuff? All right, questions online? Looks good. Okay, great. All right, so simulation modeling. So last time where we left off, we kind of talked about how industrial and systems engineering, we have the dual job of we not only have to use knowledge, we have to build that knowledge to begin with. And so whereas in a lot of other engineering, we already have models that have been provided to us, Maxwell's laws or whatever. But instead, we go into systems like these crazy systems where we really have no idea how things are going to work at all once we start putting these things together. And so before we can even start doing the engineering work, we have to do modeling work to even just understand these systems. And so we have to do both of those things together. And so that's why I kind of put ISC as sort of the intersection of science and engineering, is that we're not only doing the new processes, but we're also developing the new models and making the new inferences. So we are actually saying, when you put these type of employees in a factory that's structured this way, then this thing will happen. Whereas the physicists might tell us about light and we can take that for granted, there's nothing we can take for granted about the complex systems that we're dealing with here. So we have to build knowledge about them first before we can do the engineering. And so we're going to develop models. And we have to then, once we develop those models, say how good are our models. So we have to deal with the validity of those models. And so we talked last time, well, then what really is a model? Since we're building them, we should know what they are. I gave a bunch of examples: fashion models, animal models like for pharmaceuticals and so on, and even models, pardon me, of the atom or of the electron. And in all of these cases, I was saying the one kind of general feature of models is that they are anything, any tool you can have that answers a what if question. So like there's a skateboard in the back of the room. If I wanted to ask a question about gravity, I could probably tilt the table a certain way and grab that skateboard and I could test ideas. I could actually use that skateboard as a model for gravity in general. So that skateboard is not built to be a tool for understanding gravity, but I can grab it and use it for that. So models are not what they're built of, it's how they're used. They're anything that can help you answer a what if question. That question, that answer may not be the right answer. So you might get an answer out of it, and that answer might, once you then compare it to a real world example, you find out these don't really match up. But that just tells you that the model, or probably more particularly the hypothesis that was used to generate that model, needs to be updated, and then we can revise that. So it's not about providing the right answers, it's providing any sort of answer to give us some sort of momentum on answering a what if question. And we can develop models in the real world, like the Titanic, but it sure is nice if we can gain this insight, answer these what if questions without actually having to subject real people to the consequences of these sorts of things. And so although we learn a lot from the Titanic, we would not like to reproduce the Titanic frequently. And so that's one reason why we resort to artificial models, because they're somehow safer, they're more tractable, they're maybe less costly. But the other kind of interesting thing about that is by stripping away aspects of a model to where you're just left with the really key features of the system you're interested in, you actually can get something that's much more generalizable. So there's a lot that was learned about ships in cold waters from when the Titanic sank. And so in that particular case, if I'm studying the effect of cold waters and large ships built out of particular types of metal, then maybe I do need something that's hyper-specific, hyper-realistic. But if I'm studying ships in general, some aspect of that, then maybe I don't need all of these like complicating details about water or the type of metal or the dynamics of the ship or whatever. So we're going to talk in this class about boundary adequacy. So a model starts with whatever you put into it, and it'll be our jobs to figure out the right things to put in and the right things to keep out. So you start with a model that's a super simplistic view of the world. You add a little bit more in that expands the boundary of the things that are inside that model. And every time you add a little bit more in, you get a little bit more explainability. But eventually you have diminishing marginal returns where it's more costly to make your model complex than the benefits you get out for adding that complexity. So our goal is never going to be to add arbitrary realism to a model. We need to add as much realism as we need to be useful, but no more. At the point where we get an interesting insight, there's no reason to say, well, let's just add this other factor on top of it, which probably isn't going to change our results qualitatively that much, but at least we'll make it look a little bit more realistic. And in most cases, that's going to be extra. It's going to be too costly to do that. So we don't evaluate models by how complex they are. We evaluate models by how useful they are, and sometimes that means how generalizable they are. So in this class, it's going to be a combination of math, stats, and programming. And simulation is much more than just programming. This isn't a class about ARENA, for example. So you're going to learn about ARENA, but ARENA is just one of the many, many simulation tools that are out there. And everything you learn about ARENA is very transferable to a wide range of other sim languages that might be a little easier to use or they're just more convenient to use. But the big things you're going to learn, especially in lecture, are how to, one, build models that provide useful insights, and then two, how to make those models efficient enough to be able to run lots of replications of them in a very little amount of time on a normal sort of computer. So we don't have to resort to some high performance computer running for a month. We can run 1,000 replications of an airport on this computer, and maybe you have to go to lunch, but you come back and those reps will be over. And so to do that, stats are going to be a big part of that. So math will be a part of building the models. Stats will be a part of designing the experiments and analyzing the data that comes out of it. So most of lecture will be math and stats, and then the lab will be the programming. And that's kind of what I'm summarizing here. We're going to focus before the midterm on the math, after the midterm on the stats, during the lab on different simulation platforms. And this is largely a survey course in stochastic simulation. So each one of these, you can go into much, much greater depth. And there are courses even at ASU, say at the graduate level, where you do that. But later in your career, if you go in to do more simulation, then you'll get more exposure to this. And there are short courses and online courses and things like that. And just generally, engineering is about lifelong learning. And you might find that you really like the modeling part of it, the math part. You might find you really like the DOE part. You might find that you're really into the programming. And then you can drill down into each one of those. But hopefully you get exposure to all three in this class. All right, so that was sort of a summary of what we were supposed to take out of last lecture. Any questions about any of those basic ideas before we then start making things more specific about simulation today and start preparing you with the lingo you need for the homeworks and so on? No? All right. I was once told that they did a study that if you ask a question in a class and then you can study, there's a random variable on how long until the first question is generated. And the mean of that variable is something like 30 seconds. And so they tell you that if you ask a question, if you're really sincere about asking a question, you need to find a way to use up about 30 seconds of time, or else you won't ever get any questions. And that's just what I did. So, all right, so no questions. Okay. All right, so we're going to be talking about sim in this class. There are three major simulation methodologies: agent-based modeling, which we'll talk about in one lab in this class; system dynamics modeling, which is the main focus of the course 477, and it sort of overlaps a little bit with the mathematical modeling you learned in 470. And then the main focus of this class, which is discrete event system simulation. So I'm not expecting you to know a lot about all three of these. I'm just going to give you a brief overview of each one of these. But again, the main focus of this class is on this discrete event system simulation. But I just want you to think, when you come out of this class, even if we focus a lot on DES, that DES isn't all of simulation. So when people refer to simulation, like digital twins is really hot in engineering right now, and digital twins is much more kind of like agent-based modeling. It's sort of really high resolution agent-based modeling. So the types of simulations that are out there are going to be much more than just the stuff we talk about in this class, but we talk about a very important simulation in this class, DES. I just want to give you exposure that there's more than just this class covers. So as I mentioned, 477, which is a class that is required for engineering management students. This is also you can find courses in WP Carey that go over system dynamics modeling. You can find courses in sustainability that do system dynamics modeling. System dynamics modeling is a little bit like modeling things with ordinary differential equations, but you don't write out the math and solve the math. You build diagrams which the underlying representation are differential equations, but instead of solving them, you hit play and they're numerically integrated in order to generate solutions over time. And these ODE models are largely accounts of the average behavior of a system. So if I was thinking about what happens at an airport on a second by second basis, Monday at 9 a.m., if you look at how many people arrive at 9 a.m. and then 9:01 and so on and so forth, you're going to get a bunch of different, you're not going to get a smooth trajectory. And then if you come to the next Monday at 9 a.m., it's going to be different, and so on and so forth. But if you averaged over all of the Mondays in an airport, you would get some sort of trajectory where you'd have an average amount of traffic at 9 a.m., another average at at 10 a.m., and it might ramp up and then come back down and so on. It's those smooth averages that are represented in system dynamics modeling. So we're not modeling individuals specifically. We're sort of scaling up to model general trends. The advantage of this is it's fast to simulate and requires relatively few parameters because you're only really capturing the mean behavior of systems. The downside of that is it doesn't capture important small scale variations. And so if you think about 470, how many people have taken 470 stochastic OR? Very few. Okay, so in 470, you'll learn about mathematical models to handle things like queuing systems. And so these are largely kind of like this, where you really are sort of saying, on average, we have this arrival rate to a queue, and on average, we have this service rate of taking people out of a queue. And when you have these two averages coming in, what's the average steady state length of the line of people waiting in that queue? Well, that's a very useful piece of information for a general average trends. But if you're actually, say, running a bank or something like that, you might want to know, will my line ever get longer than 20 people? And even if the average is 7, there could be a really bad day where you get really bursty traffic and you're going to have 25 people in that line and there's not enough room in the bank. So if you're really concerned about the day-to-day variation, then these models don't capture that. They just say what happens on the average day. That's system dynamics modeling. It's largely just numerical integration of math models. And so the way those look is something like this. This is a so-called BAS model. It's a model used in marketing. And I'm not going to go through a lot of detail here, but basically this particular model, which keeps rerunning over and over, it says it's a model of a market, let's say for an iPhone or something like that. And at the beginning of time, you've got a bunch of adopters. At the end of time, everybody who's going to buy the product has bought the product, so that you don't have any potential adopters anymore, and everybody's adopted it. And you can study how many new adopters occur over time. And so you can kind of see the peak in the number of new adopters. It's a little bit like a contagion model, seeing like how many people are sick at a time. You can think of these are like people who were susceptible, and these are people who recovered, and these are the ones who are infected, or something along those lines. And so it doesn't say like, you know, from country to country to country, or state to state to state, how does the dynamics change? It just sort of says on average, in like the United States, across all states, then this is generally the trajectory that would happen as this technology is released and starts getting taken up. You know, it might have a slow rise and then a fast rise, and then it slows down again. But it describes averages, average behavior. So there's no jaggedness here. There's no randomness or anything like that. It's smooth behaviors come at the output of these models. And so to build these models, you often ask, what are the general causal relationships in a system? So this is a causal loop diagram that I took out of a paper about modeling an airport, and they listed all sorts of things that could lead to airport delays and cancellations and so on. So small scale relationships. So, you know, if I look up here, they talk about like the airport size relates to flight restrictions, and flight restrictions relate to airport delays. So airport size is some indirect relationship with airport delays, and so on and so forth. And once you have all those causes, then you start to parameterize that, and you can turn it into a dynamical model. And so this is a so-called stock and flow model, where all the boxes are like state variables in a differential equation, and all the thick lines are like differential equations. So if this is x, then this line is dx dt, and all the lines coming into it are variables that would show up in that dx dt equals equation. And so this effectively lets you set up an ordinary differential equation. When you hit play, it ends up solving for you, and it gives you an average trajectory of these airports over time. And you can tweak the parameters and see the outputs and differences in those trends. And so, they have 3 treatments in this paper where they decreased all these parameters of interest, or they increased all these parameters of interest, or they had a baseline. And they showed that the parameters of interest could actually control the average. So an increase in the parameters they selected leaded the average to go one way, a decrease in the parameters selected lead to go another way. So it's allowed them to test a hypothesis about the average behavior of the airports. Now, on any particular, this is over a long period of time. Now, on any particular day, it might be that the current arrangement of parameters might be greater than the decreased treatment or the increased treatment, but on average, the current is in between the two, and that's what's being modeled here. So that's system dynamics modeling. It's a way of mathematically capturing the average behavior in systems. Now, on the flip side of system dynamics modeling, like total other end of the spectrum, there's agent-based modeling. And this is when you really care about all of the second by second variation. In this case, you don't model average trends, you model what every single individual does in your system. So this is like a Sim City sort of thing, or it's kind of like it's basically, imagine if instead of you wanted to simulate that airport, instead of just simulating how many passengers are arriving, you actually have to simulate every single passenger that arrives. And so you have to instantiate the passenger as they come to the airport, and then you have to give them a behavioral rule that says this passenger, whenever they bump into another passenger, this is how they respond to bumping into passengers. Whenever this passenger hits a security line, this is what the passenger does in that security line. You have to do every single thing. It's very spatially explicit. And then you allow these passengers to run around. So you have so much freedom in adding complexity to these systems. So the advantage of that is you potentially can make a very realistic, or at least very complex simulation. The disadvantage is it's really slow to simulate. There's a lot of bookkeeping there, and you've got to get a lot of stuff right, and it's hard to communicate all the things you have to get right. To give an example of that, I've got, so here's, so this is sort of static examples, but I'll show an animated one here in a second. So this is an ABM of vehicle traffic. So you can see they have a simulated city grid. And although they simulated every single car, and they've got red lights and green lights that turn on certain timing schedules, it still looks a little cartoony. So it's not at the level of realism of a real city, but you at least have variation across intersection to intersection. Disease spread, so instead of having individuals the average rate of transmission. You actually have to have an infected individual meet a susceptible individual for the disease to spread, power networks, and so on. So you've got a lot of different types of agents all interacting together. And here's an airport example of this where I think if I click, it'll start. It looks really kind of artificial, right? I mean, in some ways it's complex. So basically what they've got here is a bunch of individuals arrive to airport security here, and they move around randomly, which doesn't make a whole lot of sense, but it's kind of like a null model, and I'll explain what that means in a second. And then when they happen to hit a security line, if it's open, they progress through the security line, and then they leave. And they can take stats on how many people are in the metal detector and how many people have actually left the system. So how many people are still in the airport. And so you can do things in this model, like turn on and off security lanes. And so this is like a weird way that you'd imagine an airport to run. Now you could say that we're just modeling, like the behavior of real people is so complex that it's just easier to model them as moving around randomly. You know, and the random movements represents how some of them are going to get their lunch and other ones are going straight there, and so on and so forth. But that's one way to kind of view this. The other way to view it is, and this is often the case, because it's hard to build agent-based models that are convincing representations of reality, because you have to get so much right, it's easier to build agent-based models that we would call will be a null model, like a baseline. Like you might come up with a strategy for assigning individuals to security lanes, and you run your sim of that strategy, and it produces particular numbers. Well, how do you know that those numbers are any good? Well, if you could say, well, what's my null expectation? Well, what if people just randomly, hit a security lane? What would the stats be in that case? Well, that's what we sort of simulated here. If people just did the weirdest thing possible and they just randomly bumped around, if they happened to hit a security lane, that's when they would go through. We could look at the stats of that. And if my fancy allocation strategy can't beat the random strategy, then that probably means that my allocation strategy isn't very good. But I didn't know that until I built the null model to begin with. So agent-based models are often more realistic null models than they are models of the actual system that you're trying to test. Does that make sense? Any questions about that? And I think in lab 4, you'll get an opportunity to use agent-based models and for 2 different systems, and you get a chance to sort of see how they work and how to set up experiments with them. So we will see these a little bit more. But for most of this class, we work with discrete event system simulation. And DES is, we can view as something intermediate in between these 2 different extremes. So in this case, we do model individuals in discrete event system simulation, but we don't model individuals as having agency. That's why they're not agent-based. So what I mean by that is in an agent-based model, somebody walks into a modeled classroom and we actually have to say where they're going to go when they go into the classroom. Do they go left, right, or whatever? And we have to come up with a movement rule for how they get from the door to anywhere else in the classroom. In an agent-based model or so-called process-centric model, everybody's a marble and they're sort of knocked around by a pinball machine that is the rest of the world. And so the logic is in the outside of the world. So it's kind of like if you enter the classroom, we know that everyone who comes into the classroom will eventually hit one of these seats. So maybe when we enter the classroom, we sort of flip a coin, a many-sided coin, to decide which seat they're going in and just put them in that seat. And we don't care about how long it took to walk around or whatever, because we know the process is you enter the door, you sit in the chair. And some chairs will take longer and some chairs will be shorter from the door, but it's basically random when people come in, they just go directly door to chair. So that process, door to chair, we can model and we can skip all of the little details in between. Now that allows us to still have variation. So it's not like a discrete event system simulation where, it's not like a system dynamics model where effectively everybody sits in the first chair and then the second chair and so on. It's still random which chair you go to. So we still get variation out, but we have to specify far fewer things and we still get a realistic trajectory, even though we're not modeling every single thing that happens in between door in the chair. So basically, what I'm saying here is that each entity passively moves through what we refer to as sequences of activities. It takes a certain amount of time to get from the door to the chair. It takes a certain amount of time to listen to me drone on for however long I do, roughly an hour and 15 minutes. It takes a certain amount of time to get back from chair to the door. Each one of those things are activities that are durations that we simulate. And then you can only complete those activities if resources are available. You come to the room, all the chairs are full. We got to stay in the back of the room until the chair empties up. You come to the room, I'm not here. You got to wait for me to get here before we can start the lecture. So there are resources like the chairs, me, the classroom, that you're waiting on, and that sort of determines when you can start these activities. And so, so understanding the difference between, well, understanding how much waiting time is accumulated is largely what these discrete event system simulations are all about. So we want to sort of model how long individuals, or how quickly individuals arrive to a system, how long each resource spends with every individual, and we want to measure things like how long do they have to wait in order to get to those resources. It's more realistic than system dynamics modeling. We get variation. It's faster to simulate than agent-based modeling because there's less to keep track of. And it's a good fit when we have engineered systems where we know the processes. And so if you absolutely know that you go from station A to station B, then it's easy to encode that in a discrete event system simulation. It can be a poor fit for state-of-the-art systems. Like let's say you've got some nano fabrication process where you just inject a bunch of nanobots into some fluid and wait for them to assemble something. That might be better described by an agent-based model. And it requires some background on stochastic modeling. So all the stuff that we leave out, like, you know, any idiot in middle school who learns their first programming language can write a little, app where some, turtle can move around a room in random directions and maybe eventually hit a chair. But to skip over all of that and just say, I'm going to draw a random number that is a good fit for real life for how long it takes to get from the door to the chair, that requires actually doing some probabilistic modeling of, what are the different probabilities of different timings. So it requires a little bit more mathematical sophistication than the other two. So the system dynamics model is sort of simple calculus. The agent-based model is like no math. It's just all programming. And the DES is this balance where we replace a lot of the details with a little bit more sophisticated math. And that math makes things a little bit faster while maintaining a certain amount of variation. And that's what we're going to see throughout the semester. Okay, so examples of that. So there's a really simple example. This is, you can think of this as a security line at an airport, or maybe going into a government building or whatever. I'll just stick with airport since I've been talking about airport examples anyway. And what we're going to see here, I think if I advance ahead, let me make sure that, yeah, okay. So this is what you would draw in a discrete event system simulation. So it's the process, people arrive, what's the next thing they do? They get, their ID gets checked. What's the next thing they do? Well, after ID gets checked, they either pass security and they move on to the rest of the airport, or they get kicked out and they go to wherever you get kicked out when you don't pass security. And that's, just modeling the process here. And then we have to drill down inside these blocks and actually say, well, how often do they pass security? How long does it take to check the ID? How frequently do they arrive? And so on. Once we've done all of that, we can run a sim where we can add a little bit of visualization, which makes it start looking a little bit more realistic. So we've got a document checker here, a stand where individuals, so this is our document checker resource. This is sort of a location of the individual with their document getting checked. And here's a queue where all the other individuals are waiting to get their documents checked. And we can then have the WIP, for example, the work in progress, get plotted over time down here. And we can further take that, and we'll actually see the simulation run here, and we can turn this 2D visualization into a 3D visualization down here. So the 3D passengers that are arriving and getting their documents checked, you'll actually see being mirrored up here with the 2D over here. And it might be hard to see. I might skip ahead in the video here, but there is a WIP that is being, oh, there, I advanced. So you can see the WIP here is being plotted over time. It has a lot of variation. So I sped up the time. There's a a slider here that I'm sliding up and down so I can speed it up and slow it down. So although I didn't model everything that's going on in the system, I still just by, and we'll see, it's due to the fact that I use probabilities, I still end up getting what looks to be a realistic diagram of the whip in the system here. So it's not a smooth trajectory. It's constantly sort of, sometimes it goes up, sometimes it goes down, and there's trends that kind of it follows, but it's pretty hairy. So it looks like realistic data. But if I'm showing this to a stakeholder, rather than just showing them this diagram or showing them this diagram, which doesn't look very realistic at all, this visualization, although it's pretty robotic, it still looks plausible. To, when you think about it, you're like, yeah, I get it. I don't really need to see that in this line, sometimes the person behind sometimes people aren't quite lined up perfectly, and sometimes they're checking their phone and all those things. I don't need to see all those details. It still communicates to me that there is a line of people and there's one person getting checked and there's a resource here. So it looks like a plausible trajectory you would see in a real airport, even though the programming here is pretty darn simple. So then I've got another example of that. So the model is not spatially explicit, but the visualization gives you this idea it's plausible. And another example of that is this hospital one. And this is a canned example that comes with Arena. And so we're looking overhead at a hospital emergency room. People arrive, they come in, there's a reception area, there's a lobby where they wait. There are beds that they go into treatment in. Some of them end up recovering and leave. Some of them looks like not such a good outcome over here. There's a waiting area inside here. And so the key is this looks like a realistic pattern for a real emergency room. But when I end up, and it looks like when I simulate it and visualize it this way, it looks like it might as well be an agent-based model. But in reality, when I actually look at the code, well, and it generates realistic outputs as well. So the number and system is kind of hairy, like you'd expect. It has breakdowns of different types of service and things like that. So it's a lot of very realistic numbers. But then if I look at the code here, it's really sort of simple flows here. Like in the patient room area, you secure a bed. You have to wait for the room to get prepped. You got to wait for a nurse. You've got to wait for a doctor. You've got to finally get released from the hospital, and then you record stats. And so this is a simple sequence of steps. But because there's multiple agents going through the system, and for some agents, it takes longer to get a doctor than another, and they're all happening in parallel, when I put all those agents together, then it starts looking like something more like an agent-based model with all of the craziness that goes on. But when I actually code it up, it's just a sequence of steps. It's a flow chart. So it's pretty easy to code up, but it still gives me that realism. And that's the advantage of these discrete event system simulations. And in the airport example case here, I can also expand the things that someone goes through after they pass security. And it's a relatively simple way to expand it. I just add more steps to this process and I can simulate that out. And then I can get real stats out. And the big thing I want to highlight in the stats that come out of here, these aren't just averages. These have confidence intervals. So if I look at waiting time for the people in the check for proper ID queue, there's an average waiting time and a 95% confidence interval half width. Down here in this X-ray baggage check queue, there's an average as well as a half width. So this is saying from sim run to sim run, from customer to customer, within customers, there's variation, and across simulation runs, there's variation, just like an experiment in the real world. So this gives us real world variation with not that complex of the coding. And that's really the advantage of discrete event system simulation. I think I've just got other examples where, again, you get real world utilizations, real world costs that it keeps track of. So it allows you to account for a lot of realistic things, even though the coding is not that complex. And you can use them in a wide range of applications. So here's marketing for, I think this is not for Arena, I think it's for a different program where they also have a 3D visualization of a factory where these are all coded with the same sort of process logic that you just saw. And here's a paper where they've used actually Arena to optimize, if you look at the title here, there for the picking, stochastic optimization modeling can help volunteers glean more food for food banks. And so in this case, gleaning of food has to do with there's these, if you've got a bunch of apples that are about to be thrown out at a grocery store, if you just could collect those before they're getting thrown out, then they might be able to be immediately used at food banks before they spoil. But you need a workforce to be able to efficiently go and collect those apples, not knowing which grocery store is going to have more apples than which. So you can build an agent-based model, or sorry, not a discrete event system simulation model that helps you figure out how to best allocate people to glean the amount of food here. So this is not maybe a traditional industrial application, but using discrete event system simulation to do that process. So there's a lot of generality in these methods. They're relatively simple to code, but they generate pretty realistic results. And that's why we do them. So that's kind of an overview of where we're going with simulation. The next couple of slides are getting into the specifics that will hopefully help you with the homework in the lab coming up. But are there questions about this kind of overview? The 3 types of sim, discrete event system simulation. Check back here also online. Okay. Yeah.
You go through the same, like, having to go collect all your data, like figure out what you want to collect, and collecting it, like tediously.
Well, so that's a great question. So the question was, what sort of is the burden of collecting the data to make these different sim platforms work? Does that kind of capture? It depends. So the more parameters you have, the more you have to get right. So if you are running a system dynamics model, if you're running a system dynamics model, an SDM, it might only have 3 or 4 parameters. And those 3 or 4 parameters, because they're average parameters, you might be able to just go out and get historical data and do some averaging over a time period. Like how many people got sick with COVID during the peak of the pandemic or whatever. Like just knowing that how many number might be pretty easy, and that would help you parameterize that model. Once you go to an agent-based model, you've got a lot more parameters, and it might, and that each one of those parameters might not have an easy data set. Like that might be like, how likely is someone when they're walking forward to tend to turn to the left? Well, now I'm gonna probably have to sample over a huge number of people in order to really get a good motion model there, if I really care about that. So it's kind of like the more parameters you have, the more burden you have at setting those parameters. And so DES is meant to be a sweet spot in that it has more parameters, thus more realism than agent-based modeling, but far fewer parameters than, more parameters than system dynamics modeling, far fewer parameters than agent-based modeling. And so you won't have to do as much data collection. And some of the things, and we'll talk about this later in the semester, but sometimes like if you're doing your final project, you'll say, Ted, I wanted to model this, I don't know, we'll say Chipotle or something like that. And I was able to model, I was able to take data and figure out that from the 9 a.m. hour every day of the work week, people arrive at an average of, I don't know, 20 customers an hour or something like that. But I had no way to measure how long it took to make the rice or something like that. Like it was just infeasible for me to watch that. And so a lot of times what you'd say is, well, take a guess, run your sim, and then take that guess and change it, one way or the other, and run your sim again and see if you get qualitatively different results. If you don't, then one of the things you'd write in your report is that these results were robust to parameter uncertainty for rice cooking time. But if you do find that rice cooking time really matters, then in that case, in your report, you would write an important line of future research is to properly instrument rice cooking time, because that's an extremely sensitive parameter to get right in this system. So sometimes modeling is not all about getting it right and running the model. Sometimes running the model tells you what you need to get right. Does that make sense? Yeah, question in the back? So the question was sort of, I think, is mean invariance enough when you were talking about like the outputs of these models? And it's going to depend on your research question and your predictions. Very often we're making predictions about means, like is the mean number of people when the Chipotle is set up in configuration A, do we have a mean throughput that's higher than configuration B? But as you should know, the only way to statistically rigorously compare means is to do a t-test, for example. And a t-test requires you to know variance. So in that case, I need to know mean and variance in order to compare means. So for most of the things we talk about, we're making inferences on means. But in order to do an inference on means, we have to do analysis of variance, basically, in ANOVA, which requires us to also get variance. So almost everything here, if you've got mean and variance, it's probably enough for the types of stats we'd run here. Now, if you were running an inference on variance or something like that, then you might need higher moments and things like that. But for most of the things we do, mean and variance will be enough to make a convincing argument. Okay. All right, well, we'll get into a lot more of that. I'm going to skip that attendance exercise for the moment, just to keep things on track. One hiccup that here is that Arena, well, Rockwell Automation brought out this version 16.1 of Arena. So this is a screenshot of 16.1. It's got a ribbon across the top, kind of like modern versions of Microsoft Word or whatever. This is 16.0. It looks a little bit more like older school versions of Windows. And so the textbook images from the lab, as well as many of my slides, are going to look more like 16.0. So that's one of the things that we'll have to sort of say, like, you know, when we expected, normally you'd find it in this menu, but it's actually in this tab in the ribbon. So we're gonna have to deal with that. So look out for that if you install version 16.1. In theory, you can install 16.0, but the downside of installing 16.0 is if any of your team members on your final project team install 16.1, although 16.1 can run models built in 16.0, 16.0 can't run models built in 16.1. So really kind of forces everybody to use 16.1, and I think that's the reason why we pushed the 16.1 on all the labs anyway. So that's one of the things there. The other thing is, if you install 16.1, there is an auxiliary thing called Crystal Reports Engine that in 16.0 was installed automatically. You need this thing to be installed, but I think for copyright reasons, they're not allowed to install it automatically, but they are allowed to distribute it with the installation materials. So it's a little dumb, but after you install Arena, get it all installed, you go into the Arena installer, and I've got instructions about all of this on Canvas, but you go into a folder and you run a separate installer for Crystal Reports. And then once it's installed, you finally have the complete package together. So there's that. Now, once you get 16.1 installed, you can either, like, there are these blocks that we'll learn about that are organized into different panels than the 16.0 panels. And so if I were to say to you, get a create block, well, in 16.0, we'd look for the create block in a different place. Now, you can either learn all the new places for 16.1, and I can help you with that, or as you'll learn in one of the earliest labs on Arena, you can attach panels to the 16.1 Arena. And it turns out there's this thing called old Arena templates where they have all of the old panels from 16.0 are attachable in 16.1. And once you do that, then this will match what the book looks like and a lot of the slides and everything. So all this I've kind of echoed on Canvas somewhere. So you don't need to sort of all understand what I'm talking about here, but I just want to give you a heads up that for those of you who started to install Arena, we're not going to get to Arena till lab 4 or lab 5. So you got time, but if you've looked ahead to this, then this is going to be one of the things that's going to look weird. You install 16.1 and it'll be like, did I install the right program? Because it doesn't look like 16.0. It is the right program. It does everything identically the same. They just rearrange the user interface. And so you either get used to the new interface or you kind of downgrade to the old interface. So just sort of as a tip. Okay, and so now just to sort of prep us for the first lab and the homework, let's cover some terms that we will use whenever we're talking about these models. All right, so I've used the word system quite a lot. So I'm just going to define system as a group of objects connected for some joint purpose. So I already talked about the boundary of a system as kind of all of the things that you're saying are important to the system. Things you leave outside the boundary are not going to be formally modeled. So examples, you could say, well, 100 students in a classroom with an instructor, that's a system. It's a much smaller system than 100,000 students on a whole campus during a time with no classes. So during no class, so in the second system, I might not have any instructors, but I have a whole lot more students. In the first system, which might be embedded in a larger system, but if I forget about the larger system, then this is a system by itself, which is 100 students in a classroom with one instructor. So that's what I mean, all of those things together, that's what we're calling the system. We focus on dynamical systems, so these are systems that change over time. When we talk about systems that change over time, we're going to use the word state. The state of a system is sort of the snapshot of the system at any instant. And so as the system changes over time, its state is changing. So the 5 passengers waiting in a line while 2 of the 3 agents are busy checking IDs, that's a state of the system. So once once one of these agents now moves on and is not busy anymore, one of these passengers will not be waiting anymore, and the state of the system will change because now there'll be 4 in line, and then maybe still 2 out of 3 are busy because now they're busy with this new one. So that's what I mean by state. Now we're going to use the term state variable to be a placeholder for the current state of the system. So so this is a distinction that's really hard when you're starting out, because you're tempted to say like you swap them, but they're not synonyms. A state variable is like X. You say, well, what does X represent? Because X represents the number of people currently in the system. Now, if I say, so X is a state variable. Now, if I say there's 10 people in the system, that's a state. So the current state is actually the number. So if I say X equals 10, X is the state variable, 10 is the state. So state variables are the things we use in the equations. States are the things we plot on the graphs as we plot things over time. Does that distinction make sense between state and state variable? Now, we will work with a lot of discrete state variables. Now, what we mean by that is that the discrete state variable has its state only changes at countable instants of time. So the temperature in this room is not a discrete state variable because it continuously is changing. But the number of students in this room is a discrete state variable because it only changes at the instant someone goes in or out of that door. So those instants are called events. And so events are instants of time where state variables jump. Now, discrete state variables themselves can have continuous values. So you can have things that, you could model if, let's say, the temperature of a tightly controlled oven or something like that. You might be able to model that as if it was, it's regulated at some temperature, and then you computer control it and you say, go to some other temperature, and practically instantaneously, the oven jumps to another temperature and it holds that temperature. Now, it could jump to any of a continuum of temperatures, but we still model it as jumping at instants of time. So if you jump at countable instants of time, you're a discrete state variable, even if the values you take on might be continuous. It'll be a little confusing, but hopefully most of the discrete state variables we talk about will be discrete valued as well, like number of students. That has both discrete values and moves at discrete times. Does that make sense? The discrete, or does it start to make sense? Okay. So in 475, we focus on DES, discrete event system simulations. So we're focusing only on discrete state variables. So in more complex models, we might have continuous time and discrete time together. So we would care about the temperature as it's changing continuously. But in DES models, we skip anything that's not at an event. So we just jump from event to event to event, and we forget that time is flowing in between events. And we'll see examples of that. All right, so once we have those, then we can break our process logic down, and we can talk, and I've already mentioned some of these already. We have resources. Those are things that are limited in quantity in the system that are needed for performing activities. Their availability can change over time, but we don't view them as arriving and departing. So at an airport, a document checker, even though a document checker might go on break, we say potentially there's up to 2 document checkers at a security gate in an airport. So that resource is always there. Occasionally, the capacity might change from 2 to 1 as one of them goes on break, but we're not viewing the document checkers as moving about the airport. We're viewing them as always in place, and just sometimes one disappears and then reappears as the capacity changes. So the resource capacity or availability can change over time, but the resource stands there, and they do the activity of checking the documents. And so that's just the person comes up to them, they check their document. It might take an average of 5 seconds, sometimes takes 3 seconds, sometimes takes 30 seconds. So there's a distribution of times, but we know that distribution, that's the activity, and they're the ones doing the activity. So I list X-ray scanners, TSA officers, etc. The things that come up to the resources and then leave the resources, we call entities. So they actually arrive at a system and they depart a system. So they're the things that are constantly flowing through the system. They're the water through the fountain that is the system. And they use resources. So when an entity comes up to a resource, that resource cannot be used by another entity. Other entities have to wait for that entity to leave. And that's what creates delays in the system. So, and that's what I'm just saying here, is that resources are paired with entities, and they're paired there for a duration of time called an activity, and entities that have to wait on a resource to become available, the waiting time is called a delay. So that's a fundamental difference between a delay and an activity. An activity you know ahead of time, it's the amount of time, the distribution of time it takes to check an ID, but you don't know the delays. You have to simulate the whole system to see, based on this arrival rate, what's the average delay that someone has to wait in order to even get access to the resource. Questions about that distinction, entities and delay, or sorry, activities and delays, resources and entities. Questions online? I saw an answer online, thanks for that. Okay. So passengers, luggage, cargo, these are all ideas of entities. We can differentiate between different entities by their attributes. So we can say this entity is a frequent flyer, this entity is pre-check. So those different, those things that make entities different, which might change how long they have to wait, or it might change their process, we refer to those as attributes. And so there's pre-check status, arrival at airport, and so on. And then again, activity and delay. Both of these are durations, but activities are predictable without knowing the system state, whereas delays, we don't know ahead of time until we actually simulate the system. So any questions about those terms that we're going to use like throughout the semester? Okay. All right, so an example, a manufacturing system, entities might be parts. They arrive at the system, they're assembled, they get turned into other things. So the parts are flowing through the system. They have attributes, so there might be features of the part, there might be part numbers, color, when they arrive. So these are things that are unique, perhaps to each entity. But those entities flow from machine to machine to machine. The machines are always in the manufacturing system. The parts are going in the manufacturing system and coming out. They might come out in a different form than they came in. The activities are how long it takes for each machine to process those parts. And the delays are how long a part has to sit in a queue waiting to get into a machine. Okay. So events that occur, parts could arrive, that's an event. Process could be complete at a particular machine, or a machine could fail, reducing the capacity of that resource by 1. State variables, each machine is idle or busy. So the states here are idle and busy, but the state variable is the status of the machine. So like MI, that might be the machine status. That's the state variable. And 0, maybe that's idle, and 1 is busy. Those are the 2 states that it can take on. So the state of a 5-machine system is just the combination of its 5 state variables, the Cartesian product of its 5 state variables. And so the state of the whole system might be this little vector here of 1, 1, 0, 0, 1. So 2 machines are idle, and 3 machines are busy. The current state. Any questions about that? All right, so this example highlights that you can have 2 machines here that are idle. And that might not make any sense because there's always parts that are available to do work. But because this is process constrained, these machines that are idle might need to wait for other machines to finish their work before parts are available to them. So even though parts are waiting to get access to these machines, there are no parts waiting to get access to these machines. These machines are waiting for these machines to finish. And that's what generates idle time. And we wouldn't know how much time every machine is going to be idle until we simulate the system. So things like idle time and things like waiting time for a machine, those are delays. Those are things that require us to run the system to figure out how much of that's going to happen. All right, so any questions about this example? Are the terms applied to this example? Questions online? Okay. I'll just run quickly through this. There's a college example, so ASU right here. Entities might be students. These are different ways students differ. So they differ in GPA, their major, their name, their ID number, the time they entered the class. These are all things that might be stamped like a Post-it note on every student being simulated in the system. The resources that they wait on, classrooms and instructors, activities, the duration of time they have to spend in the class. That is not the time the class starts. It's actually the length of time they're in the resource. And the delays are how long they wait before, say, being able to enter the room. So, so depending on when the previous class ends, you might be able to get into the room sooner. Events, student arrives, class begins, class ends, there's a fire alarm. All of these things change the state of the system. State variables, classroom is a state variable. It can take on 1 of 2 states, busy or idle. Instructor is a state variable, maybe takes on 1 or 2 states, lecturing or proctoring. Number of students is a state variable, can take on states from 0 to 104 in a room that has a capacity of 104. So, so those are examples there. So questions about these definitions? Okay. Good, all right. All right, so then the other thing we should become familiar with is how to graphically read some of these flowcharts and figure out where these definitions that I just said fall into them. And so the first one we see is one that looks like this little character here is we'll call it a create block in Arena, but it's actually where the entities enter the system. So inside these blocks, inside our simulation tools, we're going to specify things like arrival rate, maximum number of arrivals, etc. This square block, those are process blocks, and this is where activities happen. It's where entities meet resources. So an entity will go into here, and the entity might be arbitrarily delayed. We can build a block for that. Or that entity this process block might have the restriction that an entity can only enter the process block if a certain number of resources are available. And if they're not available, it'll put a little queue outside this block, and entities will have to wait in the queue until those resources are available. So this is actually where entities meet the resources. This is where activities happen in the system. We have decide blocks. So this allows entities to branch and take different paths. So inside these things, we could put random choices, for example, or we could have logic based on attributes of the entities. We could have logic based on the state of the system. And so entities come in one side and they come out other sides based on conditions that happen inside the block. And then finally, entities are swept out of the system by these dispose blocks here, and there's nothing that really happens inside them, but we can keep track of how many entities have gone out the dispose blocks when we want to do stats. So that's how we read, how we take these are just standard flowchart symbols, but how do we sort of fit them into the DES kind of framework? So these are where the events happen. In the create block, where arrival events happen, and the process block, that's where resource failures happen, resource completions happen, resource arrivals happen, and so on. So this is the example from Arena. Again, you could be, you've got the create block, that's where the passengers arrive. This is where the TDC, the document checker, meets the passengers. This is how frequently, so passengers may wait in line if a document checker isn't available. And then some passengers are cleared, some are not. And so we have to model who gets cleared and who gets not, or who isn't inside this block here. Okay, so events occur in these two blocks. This event are arrival events. These events are begin ID checking and end ID checking events. All right, any questions so far? No, just kind of running through the definitions. It's pretty dull, but just have to get through kind of the basics here first. All right, so we can define the entities as passengers, the resources, the agents, the activities, the time it takes to check the ID. All right, so now we're going to close here with what we actually put inside those blocks, how we actually model the time it takes to check an ID and so on and so forth. So any questions before we get into that? We're actually drilling down inside the blocks to see what those look like. Okay. All right, so that's where this term stochastic is going to come into play. All right, so if we think about this example, we want to capture realistic variation in simulated passenger experiences. So if we think about it, there's variation in the time between arrivals. There's variation in how long it takes each individual to pass, to get their ID checked. And there's variation in how likely it is or whether some individuals are cleared and some individuals are denied. So we need to tell the computer how to generate variation and how to generate it in a way that looks realistic. So I'm going to zoom in and just focus for today on this arrival part here. So how do we generate the time between arrivals? Well, then we can think as a programmer, we might ask, what are the real causal factors that determine arrival time? Like in a narrative of people arriving to an airport, what causes one person to arrive at a particular time and another person to arrive at another time? And I could set up a timeline for that. And I could say, well, we've got some individual arrives here. Let's say their flight is an hour out. So they arrived, I don't know, an hour or something before their flight for whatever reason. But as we compare them, we'd say, well, now we've got a family here and they had their first child. And this is the first time they've flown with a child. And they weren't anticipating all the extra time that it would take them to get the child ready for flying. And so they cut it a little bit closer just because they weren't quite as prepared, but they're parents and hopefully they're kind of responsible. So they still aren't quite like right when they still have a little bit of a buffer. We can compare that to a family with maybe 2 kids and they know, how long it's going to take and they're just better at getting the kids ready or whatever. So they manage to get there well ahead of time. And then, there might be somebody that in their personality, they're always arriving late. So they're over there. So we've got kind of this, a bunch of different reasons why these people would arrive at different times for the same flight. Gesundheit. Now, on top of that, there are other flights. So in our arrival distribution, we not only have to simulate the reasons why these people arrived at different times for flight 1, but we also have to model why this person arrived at this time for a later flight 2. So we need to be able to generate arrival times consistent with reality here. Now I can look at this and I can say, well, I can take a measurement from real data for an airport and I can get stats, summary stats here that we get about 5 passengers per hour. So the average time between them is 20 minutes. So I can think, well, what are different ways that I could try to generate an arrival stream programmatically? Well, one approach would be to just assume that everybody arrives with the average time in between them. So we know that on average, people take 20 minutes in between arrival. And I could just simulate 20 minutes. I get one passenger arrives, wait 20 minutes, another passenger arrives, wait 20 minutes, and so on and so forth. You could do that, but it's not realistic, right? Like this, if we really want to capture the weird things that can happen inside the airport when a bunch of people arrive all at once with bursty traffic, this just ain't gonna cut it. So they say, okay, well then I guess in another sort of very programmatic deterministic way, I could try to come up with some crazy mathematical expression that is parameterized by family size, occupation, the distance from home, the particular flight, and who knows what other variables, that if you put all of this stuff in, tells you the time before the flight that the person arrives. And for this number of parameters always tell you the same time. So you could come up with this magical thing that that manages to map all of those things, but it's going to be really hard to convince somebody that you got it right. Like whatever formula you write here, people are going to say like, well, is that really always the case? How did you get this mapping between family size and the time it takes to arrive there? And also not all families of the same size may arrive at the same time because there could be, again, things that you left out. So neither of these seem very satisfying. So what we do is we step back and we stop thinking so much like a programmer and we think a little bit more like a modeler. And we sort of say, you know what, if I was just playing a board game, there would be a strategy here. I could roll a die. And I could say, whenever it comes up 6, I get a particular time in between passengers. When it comes up, whatever, 2, I get another time. When it comes up, let's say, call it 5, I get another time. When it comes up 1, I get another time. And when it comes up, whatever number that is, 4, I get a different time. So I can just roll these die and generate these times from a distribution that I look up on a card that says, it maps from all 6 faces of the die, what are the times in between. When I do that, it starts looking kind of like a real scenario, a real output here. It doesn't look very much different. The mechanism is totally different, right? There are real reasons why people arrive at different times. It's not like it's some quantum mechanical property of airports. It's like, there are really reasons why this person arrived a little bit later than this group, but we can just roll a die to get that. And it doesn't look that different. And that is the essence of what we call stochastic modeling. It's building models that use randomness instead of deterministic rules. If I were to sort of say that more specifically here, it comes from a Greek term for guessing or conjecturing. So a lot of people think stochastic is like a synonym for randomness. It's not. Stochastic it describes a modeling philosophy. It does not describe randomness. So the idea here is that, so when the first stochastic model was ever written up in a paper, before that, all models before that were deterministic. And they said, we're going to conjecture that the fundamental process is random, even though we know it's not. But let's just assume it's random. If we can assume it's random, then we think we can actually get a better model than we would if we assume not. So it's this idea that we reduce our modeling burden by replacing deterministic parameters with a random distribution, which requires far fewer parameters. And we end up getting variation that still, if we choose the distribution right, it will look realistic enough. The same way, if you choose a distribution right in a board game, a Monopoly game or whatever, it feels kind of realistic, even though you're just rolling die. So are there questions about that idea? Replacing deterministic variables with randomness. All right, so let me just to give kind of a last let me finish up here. So what does that look like? Well, we're going to talk a lot about this later in lectures E1 and E2, but to just give you an idea of where this is going from that. Instead of thinking of a 6-sided die, imagine I had a 20-sided die. I could come up with a complex table of outcomes where, like, if I rolled 1 through 10, I would simulate a 6-sided die that was unfair. So I can take a fair 20-sided die and with this table, generate 6 outcomes from the 20 outcomes so that one outcome is much more common than the other outcomes. And I could name that outcome something related to the airport, like very long delay. So this would simulate more often than not a long delay, but then there would be other types of delays that would come out less often than that. And we would get all 6 types of delays, but we would just get this one more commonly here. And that just comes from this mapping from fair die to unfair die, the biased die. And so we can also do that with things like passing security. If I want to say that most people pass security, then I say if I roll the fair die, anything from 1 through 15 as a pass, otherwise is a fail. So I get fewer failures than passes. So I just need a fair die, and I can write a program which just maps fair outcomes to unfair outcomes. And that's how I create these models. And what we're going to learn about in lecture E1 and E2 is that inside of a computer, there is a uniform random number generator provided for free. And that is our computer equivalent of a 20-sided die. It has a whole zillion of outcomes, and we will end up writing mathematical rules that map fair outcomes to unfair outcomes. So if we want an exponential distribution of inter-arrival times, there is no exponential generator inside the computer, but there's a uniform generator inside the computer. Well, I am going to teach you how to write a mathematical expression which does the board game problem, which says if you want this, it gives you a mapping which changes the fair outcomes to these unfair outcomes. In the same way we change a 20-sided die to a 6-sided die. And that's how we do stochastic modeling in these sims. So that's what we're going to end up doing here kind of the rest of the semester. And so we're going to, our job then, now that once I give you that ability to simulate whatever probability distribution you want, then your job as a modeler will be to pick the probability distributions that are the most realistic. And so the inputs to our models are not the entities. The inputs to our models are the probability distributions. The only difference between the Las Vegas airport and the Phoenix airport might not be the processes inside the airport. It might be the distribution of times in between customers. They might be totally different in Las Vegas than they are in Phoenix, and that might change the performance. And so getting the inputs, those distributions right, that's the key thing here. And that's what we're going to call input modeling. So when we refer to that term throughout the rest of the semester, input modeling, we're referring to choosing the right probability distributions for these activities, and these discrete outcomes here. So choosing probability distributions is the process of input modeling. Inputs to models are not the entities. The entities are just water flowing through the fountain of the model. The true inputs is sort of like the rate of water flowing through that water. It's not the water itself, it's how fast the waters flow. That's the input to the model. And that's all I'm kind of getting through here. All right, so that I think is kind of the last thing here. So any questions about that? We're gonna see all those terms again as we get further down there, but I just want you to see where we're going. So I'll get to the attendance exercise here. Again, just the reminders. If you're working ahead, there's opportunities for that. Lecture B2 is a week from today. It corresponds to chapter B2, and there's an ICA for that. It's just 5 questions. And so with that, I'll only give you this one attendance exercise today. I'll put it in the chat as well. And my question for you is, what are the inputs to stochastic simulation models? So I just said that the inputs are not entities to stochastic simulation models. The inputs to the models are what? And you can summarize that in as few words as possible. Like, again, 2 words is probably good. And that's all I've got for you. So with that, I hope you have a good weekend, and I'll look forward to seeing you Tuesday. And it looks like someone asked if the attendance question was reached. I just handled that. And there's a question of can I distribute PPTX into the PDF? If the person who asked that, assuming you're online, the rest of the presentations will actually not be in PowerPoint. Like I don't write them in PowerPoint. The fundamental format is PDF. So I won't have a PowerPoint version. They're written in LaTeX, so PDF's all we got. But there won't be animations. So it's just these couple had animations, and they weren't there, but none of the animations in the PowerPoint should have covered up anything. So hopefully they're still readable in the PDF format. With that, if there's no other questions, then I will end the meeting.